Welcome again in Data Science Summit Machine Learning Edition. With me is Jędrzej Świeżewski. And hey, Jędrzej.
Hi.
And Jędrzej, the online stand is yours. Everyone just waiting for your presentation. So.
Yeah, thank you. Thank you is due to the organizers for allowing me to present the slides. And indeed, my name is Jędrzej Świeżewski. I'm the head of AI at Appsilon. And today I'll be telling you a story about Mbaza AI. This is an app that is using computer vision to aid the protection of wildlife. So I'd like to start my slides with sharing with you the information that we recently learned about, and that is that our project, Mbaza, has been selected as one of the top 10 world's most promising AI projects, contributing to the Sustainable Development Goals or reaching the Sustainable Development Goals of the United Nations. And this recognition has been given to us by the International Research Center for Artificial Intelligence, running under the auspices of Unesco. So we are extremely proud to have received this recognition. And in fact, I highly recommend, if you're interested in SDGs or in AI projects which contribute to them, to check out the report, which has been published, I believe, last week, also by IRCAI, in which they cover top 100 projects that aid or aim to help in reaching those various goals. So here's a link shortener. If you would like to check it out, please do. So now the plan of my presentation is that I'll first paint some background of why we are even in this project and how it all started. Then I'll tell you a bit about more about the project itself. I'll tell you what Mbaza is. Later we'll have a sneak peek under the hood of it, so we'll look at the data that went into it and a bit of the modeling part, and then I'll wrap up with some wider context. So let's jump right into it. As I mentioned in the beginning, I work for Appsilon, and at Appsilon we are a scale-up basically, which is steadily growing, and we're mostly focused on doing two things. One is building decision support systems, so basically applications, and we in particular focus on our Shiny technology. And then there is the other leg, which I happen to lead, which is focused on doing machine learning work. And here we are mostly doing research and development projects around the field of computer vision, but we're also involved in projects which we have a label for internally, and we call them Data for Good. So Data for Good are projects that we are doing mostly because we believe that they should be done, or it's the right thing to do, or it's a good use of our skills. So we can basically help in someone who is doing some important thing, or maybe do that thing ourselves. And in particular, in our machine learning team, most of the Data for Good projects we've been involved in recently are actually circling around biodiversity conservation. And I'm mentioning all this because Mbaza, the project I'll be telling you about, is actually an example of such a project. So it all started pro bono as a contribution to, from the company to help some ecologists, and then only later we got some partial support from various organizations, and I'll be mentioning them at a later stage. So let's jump right into it. What is this project about? So it all started in a discussion with Robin Whitelock, who at the time was a postdoc in the University of Stirling in Scotland. And he was doing research on ecology and in particular on conservation of biodiversity. And he was closely collaborating with various national parks in Gabon. So you can see Gabon roughly pinned on this satellite image. Credit goes to Google Maps, of course. And then it turned out that the way he was approaching his research was actually also applicable in many other areas. And the application we've built for him initially and then with him grew to be also used in Cameroon and in Congo, and then also on the eastern bank of the continent in Tanzania and Kenya recently. So what was he actually doing in Africa? So his main aim was to understand the changes that are happening in the ecosystems of the tropical rainforests. So already from this zoom level, you can see that the large part of the Central Africa is actually covered with a rainforest. And you can imagine that the area covered by the forest is multiple times the area of Poland, just for reference. And now this is a dense tropical rainforest, so it's very hard to use remote sensing, such as satellite imagery or maybe aerial imagery, to understand what's going on in this forest. Even to such large animals as African forest elephants, it's very hard to have a look at what they're doing because the tree canopies basically obscure the view. So the way to monitor what's going on there is to use camera traps. And in this image, you can see Robbie actually installing a camera trap on a tree somewhere in the Gabonian forest. Now, a typical scenario of using camera traps for monitoring the wildlife in those forests is the following. So typically a group of ecologists, such as Robbie or national park rangers, embark on a trip which takes 3 to 4 weeks in a typical scenario, and they basically walk through a forest installing camera traps on various key locations. So basically on trees or in some other places, sometimes on some sticks. And then after waiting for around a month, they walk on another trip, and they better be exactly noting where they put those camera traps, because they need to find them to replace the batteries, maybe replace some damaged cameras, and collect data. So by collect data, I actually mean collecting data. So they're collecting SD drives from those cameras typically, and then putting them in their backpacks. And once they are done with their trip, they typically end up in a base of the park rangers, which is somewhere in the forest. And then they open their laptops. And I should say that these are quite often quite dated laptops. And then they start, making use of the data. And what this means is that they spend sometimes 3 to 4 weeks, as they estimate, basically going through thousands of images. So the first thing they do is they classify, what animal is visible in those images. And you can see examples of 2 actual images from the dataset on this slide. There is an African golden cat and some species of monkey. So some of the images are nice, like this one. Some of them are not so nice. You'll see them in a moment. But basically, they need to sift through, in a typical scenario, 30,000 images to classify them, which animal is visible in which image. Once they have that, having the metadata of those images, so knowing where and when they have been made, they can actually go to some pretty advanced, in some cases, ecological modeling. And examples of ecological models actually done on the data from camera traps are on the right-hand side of the slide. So basically, you can do some species richness or maybe some daily activity patterns. And from that, you can understand what's going on in the ecosystem. For example, how have the migration routes of forest elephants been affected by a certain investment that was made by, for example, by a company building a new branch of its factories somewhere near the forest. Or maybe local authorities want to understand which route for a road they're planning between 2 cities will have a smaller impact on the ecosystem. So basically, what we have helped them with, so with the application we've built, does the following. It shortens the time from collecting the data to having it ready for the analysis, for the ecological analysis, from several weeks of rather tough manual work. And it's tough in the sense that it's really tiresome. So imagine spending an entire day just clicking on images which are very rich with information. It's really, really eyes training and then, hard for hard on your brain, right? It's really hard to keep attention, keep your focus. And so basically, you're very prone to make mistakes, especially in the later stage of the process. So what we've done is we've built an application that they can run on their laptops. So now, after the trip in the forest, they sit down, they open the same laptops, and instead of clicking for 3 weeks, they click one button, select the model they want to use, they run the processing, and within several hours, in a typical scenario, around a day, they have the classifications ready. And that is important for at least two main reasons. One is that it allows them to, it's conceivable now to actually scale up the surveys that they're making. So they can potentially install many more cameras, and that gives them a higher spatial and temporal resolution of the information. So they can monitor what's going on in those forests more closely. On the other hand, they can also spend more time running the analysis, and that makes it important. The important thing about it is that, well, one thing is that the analysis may be revealing more insights or maybe be even deeper. But the second thing is that they can spend more time actually making use of that analysis. So basically advising local authorities or companies who in Gabon are actually obliged to contribute to the observation of the ecosystem around their properties. So that's all well and nice. So here's a sneak peek of actually how the application looks like. So when the park ranger or ecologist sits down and gets some images classified, they can, well, see the images from the camera traps. They can possibly adjust some classifications if need be, and they can also view the classifications on a map, which is very important for a quick understanding of large amounts of data that those people are using in their research. So that's how it looks like. And I should say with something important that I haven't said yet, and that is that Mbaza is an application that we've built mostly at Appsilon with some help from external contributors who just joined the project because they liked it so much, but also some, of course, help from, in particular, Robbie, who was an academic at the time. But still, the application is completely open sourced. It's available for free. And the researchers and ecologists can just download the app and use it. Now, an important feature of this application, which makes this whole, and I would say that it's even the most important part of it, is that it operates fully offline. So, as I mentioned before, the users, the intended users of this application, make use of it in the bases of the park rangers, which are deep in the forest. And they not only don't have typically internet connection, or at least not good enough to support uploading tens of thousands of images, they often don't have electricity 24/7 even in those places. So it's very important that they can actually run this application on their laptops. And that's one of the key features of our app, and a distinctive feature, I would say. And here are some organizations listed, governmental, non-governmental, and academic, which supported the development of the application at some later stage in some part. All right, so now that I've presented the application itself, let's take a look under the hood. So basically, we'll be focusing on three areas. On the data, because of course this is a machine learning based application, so it's really dependent on the data that was used to create it. We'll have a look on the machine learning involved, and then I'll mention some features of the application itself. So speaking of the data, one of the benefits of working on the data for good projects that we've been involved in is that you get to see magnificent data sets. This is an actual image from the dataset that I just came across, looking at the performance of the model on some specific subpart of the data. So this is really awesome, and this is a part of the project I really appreciate. So it's really fun not to look at some tables with numbers, but at magnificent images like this. But of course, most of the images in the dataset don't look like that one. They look like this. And I like this slide a lot because it actually conveys a few messages kind of in one place. So first of all, the largest problem that those ecologists and researchers using camera traps are facing, and it's actually, I think all the people I've talked with using camera traps, when asked what is the #1 problem they're having, they told us the problem is empty images. So camera traps are basically cameras with automated triggers, And it's very hard to tune the triggers such that they are only triggered when they actually should be triggered. So the solution the users typically go for is tuning the sensitivity such that there are a lot of false positives. And that basically results in thousands of images which are empty or seemingly empty. And that makes using them or inferring from them very hard. So the primary use case for our application and the primary goal of those people is to filter out the empty images. Having said that, the fun part about this slide is actually that none of those images is empty. So now we go to the second part of the message that this slide conveys, because it shows in what way this data set is really tough. So let's go through the images one by one. If you look at the bottom left image, you, after a few seconds, can probably see this deer-like animal here. This is one of the species of dowkers that lives in Gabon. And the interesting, I mean, this one is pretty straightforward to notice. The challenge is that in this image, there's actually a second one. And this one is much tougher to see. And I'll tell you that it is standing right in the middle of the image. And the only way I know this is that, well, the ecologists told me that dowkers actually have a characteristically black T-shaped pattern on their, well, rear. So even though we don't see any part of the head of this animal, we only see a bit of its legs and, well, the buttocks of it, and maybe the tail. I know that the dowker is standing here. So only after you actually have this knowledge and you know what those animals look from all angles, you can actually be able to find this animal in this line, in this image. The image on the right-hand side, still at the bottom, is interesting because it hints towards the fact that when you're using camera traps in the wild or collecting data in the wild, your data set will be prone to all sorts of contaminations. And you can imagine that in the rainforest, well, it rains. So there's quite a lot of moisture and there's quite a lot of effects that has on cameras. So in particular, it destroys them from time to time, but also it sometimes, basically the water is collected on the lens and then the images are spoiled until the lens dries up again. The fun thing about this image is that it actually is not water coming from the rain that you see on this blurry area around the central piece. And I know that because I happen to have learned during the studying those data that African leopards are, for some reason, very fond of licking the cameras. So in particular, in this image, you can still see the leopard. If you kind of squint your eyes, you'll see the forehead of it in the bottom left side of that image, with the two black areas being its eyes and the characteristically round ear with a darker lining still partially in focus. The amazing thing is that both the ecologists and our model correctly labeled this image as containing an African leopard. So that blew my mind when I first saw it. The top right corner of the slide shows, well, black pixels. And this image is labeled by the ecologists as empty, but our model actually sees an animal in it. And this is something which really surprised me when I started working on this project, namely that models that we've trained on in large majority daytime images actually learn to identify animals also in the dark, sometimes completely in the dark, like in this one. So you can imagine those camera traps operate 24/7, so they basically also collect images from, from dark nights. And then sometimes they do have flashlights or some extra light source installed on them, but this is very battery consuming, so quite often they don't have any, and then the images they collect are just black. Well, they seem to be black, because the thing is that if you take this image and you process it with image processing software and basically artificially brighten it, you will start seeing an animal appearing here. So basically what happens here is that actually this image is not black, it just has very tiny pixel intensity differences, and they're way too small for a human eye to spot them, but they are well enough for a machine learning model to identify the dowker that is standing right in front of the camera. So basically our models have night vision coming from an emergent property from computer vision, so to speak. And then moving on to the slide, to the image in the top left corner, we see a phenomenon which often happens, basically some branches triggering the camera. Now, as I mentioned, none of those images is empty, and this one is neither. The thing is that the only way I was able to notice the animal in this image is that I have an image collected by this camera a few seconds earlier, and I see the mandrill, so in Polish pawian, which is walking behind those branches. And in this image, you see that, well, between those two leaves, you have some trees. So on the right-hand side, you have some leaves. And then in the image a few seconds later, some part of that area is actually covered with the gray pixels of the back of that mandrill. And this hints to an interesting phenomenon, which is deciding on what you want to label as a mandrill. So would you like actually to tell the model that it should recognize such pixels as a mandrill or not? Because I bet you that no human, if they only look at this image, will ever tell you that this is the back of a mandrill. So that's an interesting problem for designing the labeling process, basically, of this data set. And one more thing about the data that I want to tell you about is that while I've mostly talked about images, so camera traps collecting images, in fact, these days, most of the cameras don't collect single images, but rather collect them in bursts. So basically sequences of images, such as the one collected in Kenya that you can see on this slide. And here comes the small one. But also videos. And the temporal dependence of the individual frames is basically a very nice source of extra knowledge for the models that we're using, and basically helps to boost the accuracy of the predictions. Because we're not really interested in a typical scenario in predicting the the species at a given frame, but rather at a given extended moment in time. So having a global prediction for a short video or a sequence of images is well enough for the use case of the ecologists. All right, so I talked about the data. So now let's jump quickly into the machine learning underlying this. So if we go back to the fact that this application has to run in the forest, right? So on the dated laptops of the park rangers or ecologists that are there, it's immediately obvious that in almost all the cases, they won't have any GPU acceleration available to them. Even more than that, they will have maybe not the latest CPU available to them. So an important limiting factor for the power of the machine learning models we can use in this application is basically the available compute. So actually what we've been using in the application for, I think, the first year and something of its running were simply ResNet models. And it feels like, this is pretty standard basic model these days, often used as the benchmark, not the eventual model, but it was still enough for the purposes. It still got enough, gave us enough trade-off between the speed and accuracy to be actually very useful to the users. So we went with it for quite some time. Later, we've been able to add more powerful models such as Convex, but still pretty standard architectures. And a nice trick that really helped this application and made it even more usable is that after training the model, obviously in Python, we serialize the model using Onyx, and then we can actually load it using a JS runtime, so JavaScript runtime within the application. And since the application is built in TypeScript, built on top of JavaScript, it allows us to actually eradicate Python completely from this app. So this is not entirely trivial because, of course, apart from the model, there is also some pre-processing, some post-processing of the predictions that is typically done in Python. So that needed to be ported to JS. But that was actually possible. And with that, we have completely removed Python from the application. So we are only using it to fine-tune the models, train new models, but we're not maybe test the models, but we're not using it in the application. And that is very important because it basically trimmed down the size of the install, of the installer package of this application by roughly 1 gigabyte. So it feels a lot, but if you think about shipping, a Python environment with PyTorch and with all the other dependencies, that becomes just about the right number. And then what additionally it allowed us to do is that it sped up the inference roughly by a factor of 3, which in turn allowed us to kind of branch off into models that were even quicker. So they could, for example, get maybe 1,000 images and then get a prediction within minutes. Or on the other hand, they could also use larger models. So we've also been able to ship for them larger models, which would be, of course, having the better accuracy, but then still operating in the time frame that is allowed by the use case of this application. So that was an important step that we've introduced in this application, I think, late last year. All right. So now, what about the results? So how good is the model? So of course I could tell you all about the different aspects of the performance of the model, show you some plots, show you some metrics, but instead I'll basically summarize that in a typical scenario, all the models that we've trained for this data roughly have a balanced accuracy of roughly 80-ish% on a data set with roughly 20 to 30 classes. This on one hand feels maybe not that spectacular, but on the other, you have to take into account that this is already very useful for the people that this thing is intended for. And second, that as I've showed you in a few slides ago, the data set is really, really challenging. The images are very large and rich in information. So there's a lot of edges, so to speak, for the convolutions to convolve. And therefore, it's a really tough challenge to get very high accuracies on this data. Maybe also one extra factor is that while some of the animals we're looking for are elephants or giraffes, some of them are, for example, rats. And well, they are quite small in the image. So, and then they are moving very fast. So they're quite often very blurry. So this becomes a challenge in even assessing the exact accuracy of the model, because even the human labeling of it is often very non-trivial. And instead of going deeper into the details, and if you're interested in some details, please let me know. Either you can post a question, I think, in the chat, or reach out to me tomorrow at the conference. I'll be there full day, I think. So instead of going deeper now, I will basically resort to mentioning that we've published 2 papers on the subject that you see link shorteners to on this slide. They've been covered in press, in particular, in those papers. And also, most importantly for us, the application and the models underlying it received very positive feedback from the actual users who are making use of this application right now in the different African national parks and conservations. So with that said, I'd like to go to a conclusion of my presentation. And basically what I want to say is that, at this conference, many of you are machine learning engineers or data scientists, or maybe managers of various levels with a deep understanding of data science and machine learning. So all of you have skills that are extremely valuable for advancing the field, and I'm sure in the conference we'll hear a lot about recent advancements in the field and how ML is gradually growing to actually be worthy of the AI label. But they're also very valuable on the market, and we'll certainly hear about a lot of use cases, of commercially successful products based on machine learning. So I would like to highlight that the skills that you're all having are also extremely useful for people who are trying to contribute to the sustainable development goals. So they're trying to make the world a better, safer, more inhabitable place, and they could really use your help. So you have the skills that can contribute to that, and please make the best use of it, of them you can. And I've actually mixed the order of my conclusions because that was supposed to be the final punchline. But let me just mention one more thing, and that is that today I've told you about the projects we've done in Central Africa. We've actually also done recently some projects related to the Arctic Ocean and the study of plankton. So I'll be happy to chat about those if you're interested. So please reach out. if you are. And then lastly, this is a project I'm especially fond of. We've been involved in aiding the monitoring of the Antarctic ecosystem. And I encourage you to, if you're interested in learning more about this project, I encourage you to attend the talk by Andrew, which will take place tomorrow in the computer vision session. And with that said, again, you have the skills, use them. Thank you for your attention.
Thank you very much for your presentation, Jędrzej. We have 4 minutes, so I have some questions from chat. Maybe first one, what was the accuracy of the machine learning labeling model with respect to human labeling?
Yeah, so that's a very good question. It's touching on an important point. Namely, like if we, of course, the way to assess the accuracy of the model is to take the labels provided by experts and then find the labels that the model predicts and compare the two. Now, if we do that straight away, we get roughly 80%, and that's the number I've mentioned, depending on what which exactly data set it is and how many classes there are, but typically it's that order of magnitude. On data that is completely out of sample. So for example, we take data from a national park we haven't used for training, collected by a different group with different camera trap settings and protocols. Still, the important limiting factor of this procedure is that the human labels are obviously very erroneous. Like even when you look at them by hand, just manually go through them, you can immediately see that there are a lot of errors there because these are large data sets, they're hard to label, and well, people make mistakes. So basically, the way we look at the performance of these models is that we look at the next step. So this classification is needed to run the ecological models. And in one of the papers that I've flashed on one of the previous slides, we've actually compared the ecological models based on the human labels and on the machine learning labels. And we proved that they are quite often indistinguishable, which means that basically you get the same ecological models irrespective of whether you're basing them on tedious manual work or a fast machine learning inference.
Okay, maybe. Thank you for your answer. Maybe one quick one. How do you collect the time of capturing of particular image? Is it encoded in photo metadata or otherwise?
Yeah, so the way we make use of it most of the time is indeed the metadata. So basically the camera traps have settings which I think it's mostly EXIF. So basically they store, in the metadata of the image itself, they store information about its capture. But also the camera traps, some models with the camera traps have kind of a setting where on the image itself you have some metadata like temperature, daytime, and so on.
Okay.
But we don't typically make use of that one because it's, you need to OCR it, and then if it's available in the EXIF, why should you OCR it?
Okay, Jędrzej, thank you for your great presentation. Dear participants, please to remember to evaluate the lecture. And if you have any questions, I see you have, but we don't have time, sorry, to respond right now. Please ask them below in comments, and this way the speaker will be able to respond to them soon. I hope so. So
I will, so please do, or reach out to me directly. That's also an option.
Of course. So thank you very much, Jędrzej, once again, and dear participants, we will see in next presentation. So